Kinetic molecular theory is about moving molecules and some of their behaviors and statements associated with that. So one, a theory about gases that made up of small particles. They're called molecules. They're moving randomly, which means they move in all different directions. They're all over the place. They don't just decide, hey, we're all moving in this direction. They're moving in all different directions, all different angles, through a space. And they're considered high velocities compared to liquids and solids. And they move in a way that we're not used to, straight lines. Because most of the motion of particles we see is affected by gravity, and there's a curve associated with that. All right? So one, gases are small. They're moving randomly through space, and they have high velocity. So what two variables in your lab do you think that is being talked about in here? So what's a word up here, and then we can actually measure that word in lab? Right. So we can measure velocities, and how do we measure velocities? Yeah, but how? But we can't directly measure the speed. This point here, distance divided by time. We can't, but we can measure indirectly the speed of the particles. How do we do that? How do you measure the speed of particles, either moving fast or slow? How do we measure that? Somebody said it back there. Temperature, right? Temperature goes up, they move faster. Temperature goes down, they move slower. Okay? And there's a relative definite proportion between those, we'll see. Okay? Is there anything else in there? So we got temperature. Is there anything else in there we can measure? Okay, we'll go on. Maybe a lot of these repeat themselves. There's no attraction between the gas particles, basically. They're saying if they come in close proximity to one another, there's no intermolecular forces of attraction. Okay, that's what they're saying. That these gases, like oxygen. What do you know about oxygen and nitrogen? Those two specific gases in general, about their attraction for one another. Are they polar? Into two nitrogens hooked together, the same electron. So they're nonpolar, and there's no hydrogen bonding. So the only thing they have going for them is dispersion forces. Plus they're pretty small in weight. So they're just basically saying there's no attraction between these particles. Any questions you have on that? Okay. All right. That's something we really can't measure in the lab when we take a look at that. All right. Here's the next two. The volume of a gas particle is extremely small when you compare it to the space it occupies. So what they're saying is pretty much insignificant. It's kind of like if I get on the scale and I put a penny in my pocket, before and after I got on the scale, what's the scale going to read? Same. Yeah, unless it's one that measures to the, those are just spring scales, and they're insignificant. That penny or 2 pennies is insignificant. Okay? It's kind of like an electron. Electron's insignificant to the weight of a molecule, right? Because what makes up the weight of an atom? The nucleus is neutrons and protons. So it's insignificant in the whole scheme of things. It's insignificant. Doesn't. So, what are some things in here that you can measure in the lab?
Volume.
Volume. You can measure volume. You can see a change in volume. Did you guys in your lab, did you guys see a change in volume? Yeah. Okay, is there anything else? So we got volume and temperature. Anything else that we can measure? Yes, you can in an indirect way. You can measure collisions. So how do you think collisions are measured of gases? What's that?
It wouldn't be the force.
It's a force over an area. So that's the definition of this.
Surface
Yeah,
area.
it's basically the force over an area is this thing we can measure. Pressure. Air pressure. Because guess what? The more collisions, do you think you have more pressure?
Yes.
Yep. Smaller collisions, less pressure. More forceful collisions, more pressure, right? Less forceful collisions. Okay? So that's a key in helping you explain some of your what's happening. Okay? They're said to be elastic, and elastic means there's always a rebound that is, it goes back to the same speed. And the only example, that's a good example, did you guys ever play Pong?
Yeah.
That's the game that we started out with, Pong. Hey, come over, let's play some Pong. Hey, I'm better than you in Pong, come on over. Sometimes you'd have 2 paddles, sometimes you have 3 paddles, right? The old version. Yeah, you had multiple versions, man. That's just one. We had 2 paddles, 3 paddles. Okay, pretty sophisticated, let me tell you. Okay, had to start somewhere. They're elastic, so that Pong goes back and forth. When it hits, it gets speed back right away. So that's what we assume gas particles are like. They don't really lose any steam when they have collisions. Okay? All right, so again, this is pressure, right? Okay, all right. And then the last one bases on temperature, and it says, the faster the particles go, the higher the temperature is. The slower they go, the less temperature is associated with it. Because that's what temperature is. Temperature is a measurement of average kinetic energy. Okay? We're going to find out in this chapter where there's no kinetic energy. So, of a particle, when is there no kinetic energy?
Absolute zero.
When what?
Absolute zero.
Yeah, well, you're getting ahead of me. When something's at absolute zero or no kinetic energy, what do we know about the particle?
It's not moving.
It's not moving. They haven't got anything to the point where it doesn't move. They've never got it cold enough to where a particle doesn't move. It's still some motion there. Okay? So, which is kind of interesting. So these are your 5 statements. We've talked about 3 statements, volume, temperature, and pressure. There's a 4th one that's throughout the whole thing they talk about. Talk about here. They're in there. Especially the top one. No, both of them. 1 and 2. They're in 3 and 4. And they're in 5. Which word comes up in all of those? You can look at your notes since you have them. Particle. So how do you think we measure particles? Moles. Right? That's how we measure how many we have, is based on moles. So now you've got 4 things that you guys can talk about. Pressure, temperature, volume, and moles when you are looking at your sample. So if you have a closed system, does the number of moles change? No. When you have an open system, yes. So you think, what's a closed system? Closed system doesn't lose any air, okay, in the process of the experiment. An open system is going to lose air, or can lose air, or gain air. Does that make sense? So, and I explained a little bit more to you guys, but these are things in which you would do to show your drawings, and then you explain your phenomena that's happening. Why does the syringe, don't tell me, but you're going to have to explain it, but why does the syringe go back to its original volume? Okay? So again, you have some things you're changing, some variables changing. You've got 4 variables: volume, temperature, pressure, and volume, temperature, pressure, and number of moles. Okay? The arrows represent what about the molecule?
Speed.
It's temperature.
Oh,
Right?
yeah.
It's temperature. Okay? I had somebody bring up a drawing and all the arrows were going down. That's really not a good representation of random. Random means they're going all over the place. Okay? Now you guys don't have to be perfect when you draw it proportionally. I just did this because that's what air is proportionally. It's 4 parts nitrogen and 1 part oxygen. So it's up to you. You don't have to get to that point where you would do that. I'm more interested in you making the drawings. These drawings don't have to be perfect. Some people are taking way too long of drawing a cylinder, making sure it's exact replica. Don't have to do that. Okay? And so then what you're going to do is you're going to show like before and during and after, if that applies, or before and after, if it's just 2 processes that you're looking at comparing. So, makes sense? And so you've got 6 of them to identify. Here's the 6. The first 3, I think, are the easiest. I think this is the easiest of the 3. I think this is next easiest, and then I think this is third. And then they get a little bit more challenging. I think 8 and 9 are the ones that are going to be a little tougher to explain, but I think you do. So, you can probably start with 1, 2, and 3. You don't have to do it in order as long as you identify which one you're doing. Any questions? Was everybody here to do it? Okay. All right, you guys can work through that. I didn't give you much time. It's going to be due on Friday. Hey, I'm seeing on labs, I'm seeing almost the exact wording on some labs of lab partners. Okay, I mean, pretty much it's copied, is what I'm saying. I mean, when I read it, it's like every word's the same. It's copied. And you say, no, I did it on my own. Oh, I did it. Well, what's the odds of you doing it on your own being the same? Exact same. No. So, guys, I don't want to see that on this. Okay, if I see that, exact copies in that, what I'm going to do is both grades are going to be 0. So if you're going to give your paper to somebody, realize that your paper could be a 0. Because if you're giving it to them, and they're copying it down, okay, so a lot more of that's going on. It needs to be, okay?
Do we do this on our lab paper?
What you'll do, and it's kind of like in English where you kind of do a rough draft. What I would do,
Just to rewrite it?
well, what I would do, I mean, if you want to do your drawings, kind of just get an idea, kind of what's going on, and then you can make maybe on a final copy make better drawings, because it doesn't take long to make a drawing or anything like that.
Okay.
Does that make sense? I would say it would be kind of like English. You'd be like, all right, I'm going to make this drawing. I know it's not going to be perfect, but it gives me, you visual learners, this is right up your alley. This is like, boom, I can do this. I can figure this out.
Do we just draw random particles?
So, Ava, like that previous one I had up here, just draw them as, they're all diatomic. So all the air particles in this room are diatomic. There's a little bit of CO2, there's a little bit of water vapor. And water you would draw like that. But they're pretty much diatomic. So if you just draw the diatomic ones.
But how would we know what's in the bowl?
It's these. It's air. So you just draw so many of those. And
Draw before, during, and after.
yeah. You know if it's a closed system, you got to draw the same number. Okay? And if it's the same temperature, you got to draw the same length of arrow. Right?
Mm-hmm.
And then you've got air on the outside. So I've got air on the outside too. If the air on the outside helps me explain the phenomena, I'm going to do that. If it doesn't explain the phenomena, then I won't do it. Okay, there's a couple in particular that explain the phenomena by drawing the arrows on the outside. Okay? So, all right.